You are about to embark on a study of the branch of computer science theory known as automata theory or language theory. We're going to follow fairly closely a one-quarter course I gave at Stanford a few years ago. Its traditional number is CS 154. This theory plays an important role in computer science. I am aware that many students don't see the importance of a mathematical approach to CS. The feeling is, just let me near a keyboard and let me code. It's quite common. In this introductory video, I'll try to give you some reasons why you should learn the material contained in the course. A number of years ago, Stanford took a survey of its graduates 5 years after they got their undergraduate degrees. What they wanted to find out was whether Stanford was teaching stuff that they actually used in their jobs. So computer science graduates naturally cited our introductory programming courses as the one they used most. No surprise here. Next came our sophomore level courses covering basic data structures and algorithms and systems software. Again, no surprise. But after the required courses, we found that CS 154, the automata course on which this set of videos is based, was second after the database course. It was cited by 3 times as many as cited the introductory AI course, for example. So I want in the next few minutes to try to explain what it was about automata theory that impacted what our former students were doing in their professional lives. So let's see some of the ideas we're going to learn about in the course and how they appear in practice. One very commonly used idea is the regular expression, a simple notation for describing many of the patterns that arise naturally in practice. Many pieces of software that you might find yourself working on in the future need a simple input language to describe patterns. So you might well find yourself implementing some form of regular expressions. For example, many Unix text processing commands use a variety of regular expressions. This expression describes a line of text that has a letter A followed by any number of characters followed by the letter B. For a more modern example, the XML document markup language invites us to describe the structure of documents by a DTD, or document type definition. The DTD language consists of descriptions of elements such as the example given here. A person element consists of a name element, followed by an address element, followed by any number of child elements. Finite automata are another topic we'll see early on. They are, in fact, the way regular expression-based languages are implemented. They also have been used for decades to model electronic circuits, and in particular to help design good circuits. They have also been used to model protocols, and we'll give some examples later in this course. Especially, finite automata underlie the body of techniques known as model checking, which has been used to verify the correctness of both communication protocols and large electronic circuits. Another important aspect of the course is the context-free grammar. These are used to put a tree structure on strings, typically text strings, according to some recursive rules. They are an essential for describing the syntax of programming languages and are a part of every compiler. They also play an important role in describing the syntax of natural languages and are used in software that does machine translation and other natural language processing. And the DTDs we mentioned in connection with regular expressions are really context-free grammars. It is the single rules of a DTD that look like regular expressions. The topics we just mentioned are essentially tools for doing simple but important things, but there is a second broad theme in this course. There are fundamental limitations on our ability to compute. A computer scientist should be aware of these limitations, because only then can you avoid spending time attempting something that is impossible. One limitation is undecidability. There are problems that cannot be solved by computation. For example, you might imagine you could write a compiler that would refuse to compile programs that printed out dirty words. Even assuming you had a precise definition of what words were dirty, you can't do this. We're going to prove that there is no way to tell whether a program will ever print a particular word, or even whether it will ever print anything at all. And we also need to know about the class of problems called intractable. These are colloquially problems that we can solve, but whose solution takes time that is exponential in the input size. These problems generally need to be finessed in some way, such as by approximating the solution. The reality of the theory of intractability is quite a bit different from the colloquial version, but while the undecidable problems have been proved not to have any solution, for the intractable problems we have very strong evidence that they require exponential time but no proof. We'll explain all this when we get to the theory of NP completeness as the culmination of this course. So another thing you'll take away from this course is the ability to navigate the space of problems that you might encounter in a life of creative software construction. You will learn how to determine that a problem is undecidable and how to determine that it is intractable. That lets you avoid the problem altogether in the first case and to modify your approach in the second case. There are several less concrete benefits to this course. First, you will improve your skills at proving facts, especially inductive proofs, of which we'll do several in great detail. Now, I'm not one of the people who thinks that formal proofs of programs will ever be a serious software methodology. But as you construct code, you should have a sense of why what you're doing works the way it is supposed to. Often the trickiest parts of a program deal with trees, graphs, or other recursive structures. Understanding inductive proofs lets you at least formulate a reason why you think your method works, even if you don't try to dot the I's in a formal proof. We're also going to learn about a number of important abstractions: finite automata, regular expressions, context-free grammars, and varieties of push-down automata and Turing machines. Some of the essential parts of this course are proving equivalences among the models. That is, any example of one model can be simulated by some instance of another model. The process of simulation across models is essentially the same as the modern approach to programming in layered abstractions, where you write programs at one layer using the primitives of the layer below. At Stanford, I found that a number of people taking the automata course were not computer scientists at all, but were mathematicians by inclination. That's cool. Welcome to those of you out there. I probably won't do things quite as formally as you would like, but more formally than the typical computer scientist likes. However, be warned that some in the past have found the subject sufficiently interesting that they saw the light and made major contributions to computer software. A case in point is Ken Thompson, the fellow who gave us Unix. Before doing Unix, Ken developed an interest in regular expressions and saw that they were an important part of a text editor. He worked out efficient ways to compile regular expressions into programs that could process text, and his algorithms are an important part of what we teach about the subject today. It should be no surprise that regular expressions form an integral part of so many Unix commands, and that these commands give more flexibility and power to Unix users than did those of earlier operating systems. Another interesting case is Jim Gray. Jim, before his mysterious disappearance, gave us many important ideas in the database field, including two-phase locking for concurrency control, for which he won the Turing Award. But I knew Jim when he was a student at Berkeley, and I was on leave there for a brief period. He did a thesis on two-way pushdown automata. We're not going to talk about them. They turn out to have been a backwater of the theory, and I'm sure Jim would agree. But they are related to ordinary pushdown automata, which we will talk about in connection with context-free grammars. What is interesting is that Gray told me quite a bit later that he decided to become a computer scientist because automata theory intrigued him. Only later did he switch into database systems, and I believe that the experience he got dealing formally with automata made him more capable as a designer of several very innovative systems. So here's a summary of what will be covered in the course. We'll start off with what are called regular languages. A language is just a set of strings, for example, the set of character strings that are valid Java programs. The regular languages are exactly those sets of strings that can be described by finite automata or regular expressions. This discussion will also introduce the important concept of nondeterminism, machines that can magically turn into many machines that each do something independently but with a coordinated effect. This model of computation is fanciful, to say the least, but we'll see it plays a really important role in several places, including design of algorithms and in understanding the theory of intractable problems. We're then going to turn to properties of the regular languages. These properties include the ability to answer certain questions about finite automata and regular expressions that we cannot decide about programs in general. An example would be to tell whether a device makes an output in response to even one input. You can't tell for programs in general, but you can for finite automata. It is this tractability, our ability to understand what simple formalisms like finite automata or regular expressions do, that make them so very valuable when they can be used. We're also going to talk about closure properties of regular languages. For example, the union or intersection of two regular languages is also a regular language. The next big topic will be context-free languages. This is a somewhat larger class of languages than the regular languages, and they enable us to do things that you can't do with regular languages, such as match balanced parentheses or XML tags. We'll talk about two ways to describe such languages. First, by context-free grammars, a recursive system for generating strings, and then by pushdown automata, which are a generalization of the finite automata that we'll use for regular expressions. We'll then repeat our examination of decision properties and closure properties for this larger class of languages. Many of the things we can tell about regular languages that we cannot tell in general, we can also tell about context-free languages. But there are unfortunately some exceptions. Similarly, many of the operations under which regular languages are closed also yield a context-free language when applied to context-free languages. But again, we lose some operations. For example, context-free languages are closed under union, but not intersection. Next, we take up the largest class of languages that we can reasonably say can be dealt with by a computer, the recursively enumerable languages. We also look at the smaller but important subset of the recursively enumerable languages called the recursive languages. These are the languages for which there is an algorithm to tell whether or not a string is in the language. We introduce the Turing machine, an automaton in the spirit of the first kinds of automata we meet, finite and pushdown automata. The Turing machine is, however, much more powerful than either of these. In fact, it is as powerful as any model that has ever been thought of to answer the question, what can we compute? The payoff for the study of Turing machines is that we can answer the question of what can be decided by computation, or what can be computed by any means at all. We shall develop tools for showing that certain problems cannot be decided, that is, answered by a computer. The example we already mentioned, does a program print a dirty word, should give you an idea of what we can achieve. Finally, we're going to cover the theory of NP completeness. The critical question is, what can we do with an algorithm that runs in time that is some polynomial in the length of the input? It would be lovely if we could distinguish between problems whose best algorithm took, say, n cubed time from those that could be solved in, say, n squared time. But no theory has ever been devised to be that precise for general problems, although the best running time for some problems is known. Fortunately, we can learn a lot by dividing problems into those that can be solved in some polynomial amount of time from those that apparently require exponential time. We'll give you the tools to do this, and Turing machines are the tool you need to build this theory, as well as the theory of what can be computed at all. This course follows the third edition of the textbook I wrote with John Hopcroft and Rajiv Motwani. You do not need to buy this book. The homeworks and exams will all be based on what you can learn by observing the slides and listening to my commentary on the slides. Okay, the following is optional and depends on what we decide to do about the page references in the homeworks. You will, incidentally, find as you do the homeworks that there are explanations when you make a mistake. These explanations refer to pages or sections in this book, but you do not need the book since the explanations, like the course material itself, are designed to be self-contained without your having to read the book. I ask one thing, however. Please do not download a free copy from a file sharing site or delete it if you have already done so. This book was published by Addison Wesley under a contract that dates back to 1967. At that time, there was no internet and it wasn't all that easy to produce books. Addison Wesley invested a good deal in the production of this book and its predecessors, and they deserve to recover their costs. It is stealing to download a copyrighted work without paying. There's no two ways to look at it. Admittedly, the world has changed, and recently I have started to put books on the web for free, download from my own Stanford web pages. You are welcome to what is freely given, but please do not take what is not offered gratis. Today we begin with an informal introduction to finite automata. I'll offer some brief remarks about their uses and then move to an extended example of an automaton that describes how a game of tennis is scored. The finite automaton is a mathematical model, but fortunately it is a model that should be quite familiar. You can think of it either as a graph or as a table. The finite automaton is simple because it stores only a finite amount of information. That can be bad, because in many applications there is no limit on the amount of information we need to remember about what has happened in the past. When that is the case, the finite automaton is not a useful model. But the finiteness of memory is great when the model can be used, because we can do a number of things with finite automata that we cannot do with programs in general. For example, given a program, you cannot really tell anything about it, what it does, or whether there is a shorter program that does the same thing. However, you can tell whether two automata do the same thing, or whether there is a smaller automaton that does the same as a given automaton. You can also tell whether an automaton does anything at all. That ability lets us tell, for example, whether there are input sequences that cause an automaton to get to an error state, which in turn lets us check whether protocols or other simple systems have flaws. A finite automaton is built around a finite collection of states. Each state has a name, and that name represents what is remembered about its history. States change in response to inputs. Inputs are either characters if we're doing something like processing text, or events if we are modeling something like a communication protocol. The rules that give the new state for each current state an input are called the transitions. The finite automaton is useful in a number of computing applications. We mentioned the design and verification of communication protocols and digital circuits. And together with the related formalism called regular expressions, they are important in text searching algorithms. They are essential for the portion of a compiler that breaks the input into tokens, identifiers, keywords like if, and so on. You find automata and regular expressions in many other applications as well, typically where simple language is needed to describe patterns that are sequences of symbols or events of some sort. To see the power and also the limitations of a finite automaton, we shall take up an example, scoring a game of tennis. If you don't play tennis, it's almost like ping pong, except you are really tiny and you stand on the table. Depending on which page comes first in response to your search query, you'll find it was invented in the 12th century or in 1879 by people who evidently had too much time on their hands. The scoring system is arcane, with matches consisting of sets, which consists of games. Games consist of points where one player or the other wins by causing the other player to hit the ball off court or into the net. We'll talk about scoring a game. One player is server throughout the game. To win the game, you must have at least 4 points, but you also must win by at least 2 points. The states we are going to use for the scoring automaton represent the numbers of points won by each player, and they have strange names, which we'll see as we go. The inputs are events in which one player wins a point, S for the server wins, and O for the opponent wins. It is common to represent a finite automaton by a graph, with nodes for states and arrows labeled by the input for transitions. Here's the first state of the automaton that scores tennis games. The name of the state is love. You may ask, what's love got to do with it? But that's what 0 is called in tennis. The state love represents the history in which nothing has happened, and we indicate that history begins with this state by an arrow labeled start. The first point will be won by one of the two players, so there are two transitions out of love, one labeled S, the other O. You might think the names of the states would be 1-0 and 0-1, because the server's score always goes first. But they're not. In tennis, there is the fiction that you score 15 for winning a point, and 0 isn't 0, it's love. The next point can lead to 3 states, 2 where one player has won both points, and 1 where they're tied at 1 each. Here are the states with their names. There is something interesting about the 15-all state. It has forgotten how we got there. We know the sequence of inputs was either SO or OS, but we don't know which. It doesn't matter, of course. That's a good thing about finite automata. They only remember what must be remembered. In state 15 all, the question of who won the first of the 2 points can't have any effect on the outcome. After another point, there are 4 new states the game could be in. They have the expected names, except people are too lazy to say 45, so they just say 40. Now let's look at the transitions from the state 40 love. The server is well ahead and can win on the next point. If the server wins, we'll go to a state indicating that win. The game is over and the automaton has no further moves. We indicate this output of the automaton by calling the state a final state, and we indicate it as final by a double circle. There is another state reachable from the state love 40 if the next input indicates the opponent won the 4th point. There are 3 other new states as well, called 40-15, 30 all, and 15-40. Each indicates that 4 points have been played, with 3, 2, or 1 of these points won by the server. From the 40-15 state, if the server wins the point, we go to the server 1 state. But if the opponent wins the point, we go to a new state called 40-30. A similar thing happens from 15-40, and from 30 all, we can go to either the 40-30 or the 30-40 state. Now let's look at the state 40-30. If the server wins the next point, they've won the game. But if the opponent wins, then the game is tied. The name for this state is deuce. The deuce state is quite interesting. It remembers that the game is tied, but it remembers neither the sequence of wins and losses of points, nor even how many points have been played. And the 30-40 state is handled similarly. Next, consider what happens in deuce. You have to win by 2 points, so it is impossible for either player to win immediately. If the server wins the next point, they are ahead by 1 point, although we don't know how many points in total have been played. The strange name for this state is add-in, or advantage in. In refers to the server. Symmetrically, if the opponent wins in state deuce, we go to state add-out. The out refers to the opponent. Then in state add-in, if the server wins the next point, they win the game. But if the opponent wins, you're back to deuce. Likewise, from add-out, a server win puts you back in deuce, but an opponent win gives the opponent the game. We can now look at the entire transition diagram for the finite automaton. While most of it just allows flow away from the start state, the loops involving deuce, add-in, and add-out, that is, these, they allow for cycles and for an infinite number of possible strings of S's and O's to lead to one of the final states. The job of an automaton is to process strings of input symbols, or input strings. We always begin at the start state and we read each input symbol in order. For each input symbol, we follow the transition from the state we are in to discover what the new state is. We accept the string if we wind up in a final state after processing the entire input. Here is an example. Here is our input string. It represents a game in which the server and opponent alternate winning points until the very end, when the server wins 2 in a row. We'll mark the current state by the star, and initially the current state is the start state. That's where all finite automata start out. The arrow indicates which input we are about to process. So here we are about to process the first event where the server wins the first point. We're going to follow the transition out of the state love, labeled S. Here we've made the first transition. The next input is O, and we're in state 15 love. The transition from that state on O is to state 15 all. In state 15 all, we see another S on the input, so we go to state 30-15. And O takes us to state 30 all. Then on S, we go to state 40-30. From there, we go on O to deuce. And from deuce on S to add in. From there on O back to deuce. And another cycle on S and O between add in and deuce. Now come the first of the 2 S's. This S takes us to add in again, but the second S takes us to the server win state. Good going, server. Now let's get a bit more formal. The job of a finite automaton is to process strings of inputs and accept or reject them. It accepts the string if it leads from the start state to a final state. Accepting state is a synonym for final state. A language is simply a set of strings in the formalism used for automata. The language accepted by an automaton A is denoted L of A. In our tennis example, we called the two states where one of the players wins the final states. In that case, the language of the finite automaton is the set of strings of S's and O's that end the game, no matter who wins. We could change the set of final states, say by making only the server win state be final. Then the automaton would have a different language, the set of strings of S's and O's that lead to a win by the server. Or we could make only opponent wins be final and have the language of ways the opponents can win. We are now going to express the ideas behind finite automata more formally. We'll see how to represent finite automata either as graphs or tables. They are two representations of the same idea. And we're going to do a few proofs in considerable detail and learn some useful proof techniques, especially inductive proofs. An alphabet is simply a finite set of symbols. There are many examples. Two standard alphabets we see frequently are the ASCII and Unicode alphabets. An alphabet we'll use frequently is the binary alphabet, consisting of only the symbols 0 and 1. We'll also sometimes use alphabets of letters like ABC, and in the tennis example we use the alphabet of outcomes consisting of the letters S and O. Each protocol has a set of signals, and the set of all signals used by a protocol is also an alphabet. Strings are the usual data type you've seen in languages like C or Java. That is, a string is a sequence of symbols chosen from some alphabet sigma. The strings over sigma are those strings whose symbols are each members of sigma. For example, 011 is a string over alphabet 01. It is also a string over alphabet 0, 1, and 2. It just happens not to have any 2's. Unlike programming languages, which typically put quotes around strings, we're not going to do that. And even though strings are lists of symbols, we're not going to separate the symbols by commas or other separators. We'll just write down the strings like this. We use the expression sigma star for the set of all strings over the alphabet sigma. The length of a string is the number of positions in that string, and a special string is the empty string, which has length 0. We represent it by epsilon. For example, the language 01 star consists of all strings that can be made from the symbols 0 and 1. For example, epsilon, the empty string, is in this language. There are two strings of length 1, the strings 0 and 1, and there are four strings of length 2, and so on. Notice that we do not make a distinction between a symbol like 0 and the string of length 1 that consists of a single instance of that symbol, the string 0. We trust that context will make clear which we mean. Programming languages do make this distinction, so in C, for example, would put single quotes around the 0 if we meant the symbol or character 0, and would put double quotes around it if we intended the string consisting of only the 0. Languages are sets of strings, and they can be finite sets or infinite sets. The only limitation we place on languages is that there is some alphabet, that is, finite set of symbols, from which all the strings in one language are composed. Here's an example of a language L we're going to meet several times. Its alphabet is 01, and it contains all strings of 0s and 1s that do not have two consecutive 1s. So the empty string is there, and both strings of length 1. Of the strings of length 2, all are there except 1, 1, because that obviously has two consecutive 1s. 5 of the 8 possible strings of length 3 are there, as are 8 of the 16 strings of length 4. Here's a little puzzle for you to think about. For length 0 through 4, we see there are 1, 2, 3, 5, and 8 strings. Do you recognize the sequence? And can you extend it to strings of length 5, 6, and so on? And in particular, can you prove that your prediction is correct? Now we'll give the formal notation for deterministic finite automata. There is a finite set of states, and we usually use Q as the set of states. Don't ask me why it's Q, it just is. And there is a finite input alphabet. The traditional name for the input alphabet is sigma, again for no known reason. There is a transition function, which we'll discuss on the next slide. It is the guts of the automaton, since it tells us how the automaton moves from state to state in response to inputs. The traditional symbol for the transition function is delta. One of the states in Q is the start state, and we designate it Q sub 0 typically. And some of the states are designated final states, or synonymously accepting states. The final states are typically denoted F. The thing that makes the automaton work is the transition function. This function, usually denoted by delta, takes 2 arguments, a state Q and an input symbol A. It gives you back the state that the automaton goes to when it is in state Q, and the next input symbol to arrive is A. The function delta is total. That is, it has a value for every state and symbol. There are examples of automata where we really don't want to continue in certain situations. For example, our tennis automaton did not have transitions out of the 2 states where one player or the other has won the game. To fix up such situations, we have to introduce a dead state. A dead state is a state that is not accepting and that has a transition to itself on every input symbol. Once you get to a dead state, you cannot leave it and you can never accept. So dead is a pretty good description of what is going on. We're going to use the abbreviation DFA for deterministic finite automaton. The deterministic means that there is a unique transition for every state and input symbol. We're going to meet nondeterministic automata soon, and there it is possible to transition to many states from one state on one input. Now, back to the matter of a dead state. Here's our tennis example, and you can notice that the 2 accepting states do not actually have any transitions out. So we add a dead state, and all the missing transitions go to that state. The transitions from the dead state are to itself on all possible input symbols. Like the tennis automaton, we can represent any finite automaton by a graph. The nodes of the graph are the states of the automaton. The arcs are the transitions. There is an arc from state or node P to state or node Q labeled by all the input symbols A, such that delta of P and A is Q. For example, this arc would be present if delta of P and A and delta of P and B were both Q. We represent the start state by adding an arrow labeled start into that state, and we indicate final states by double circles. This is an interesting example of an automaton that processes text. The goal is to recognize that the string read so far ends in ing. The start state represents the condition where we have made no progress toward seeing ing. If, in that state, we next see I, we've made some progress, so we go to the state that says I was the last symbol seen. Otherwise, we stay in the start state because what we've seen so far is no help in seeing ing. Now, from the saw I state, if we next see an N, then we have made more progress. We go to state saw IN. If we see another I in state saw I, then we've not made progress, but neither have we lost ground. We may be reading a word like skiing with a double I. Thus, the transition from state saw I on I is to itself. On any symbol other than I or N, we go back from saw I to the start state. In state saw in, if we next see a G, then we win. We have just seen ing as the last three symbols, so we go to the accepting state saw ing. On the other hand, if from state saw in we next see an I, then the pattern in is broken, but a new pattern beginning with I has started, so we go into the saw I state. On any input other than I or G, including N, we have no progress at all, so we go back to the start state. And finally, from state saw ing, we can only go to state saw I if the next input is I, and otherwise we must go back to the start state. Here is an automaton that represents the simplest possible protocol for sending data. The program is in one of two states, ready and sending. It starts in the ready state. Eventually, it gets a signal that some data has been loaded into its buffer, and at that point it enters the sending state, where it does what is necessary to transmit the contents of the buffer. The receiver will send back an ACT signal when the contents are received, in which case we are ready to return to the ready state. However, if the receiver is down, we may instead get a local timeout signal that warns us something is wrong and the buffer must be retransmitted. This automaton is not complete. There are no final states because the automaton is designed to run forever without rendering a decision. Also, there are missing transitions. It is okay to ignore ACK or timeout signals if you're in the ready state, staying in the ready state. However, a data signal in the sending state is an indication of an error, so we might want to go to an error state. And the error state is a dead state, so we need transitions to itself on any of the three inputs. A typical question that is asked about protocols is whether you can get to an error state. We could, for example, make the error state be final, and then ask if the language of the automaton is empty. As we shall see, there is an algorithm to tell whether the language of a finite automaton is empty, a question we could not ask about programs in general. In this example, however, it is really easy to see that there is a path in the graph from the start state to the final state, so its language is not empty and errors are possible. For a running example, we're going to use this automaton. Its language is the set of binary strings that do not contain two consecutive ones. State A is where the automaton will be whenever the input string seen so far is good, that is, it contains no consecutive ones, and also, in state A, it does not end in a 1. Surely the state should be the start state, since when no input has been received, there are not two consecutive ones, and moreover, the input so far does not end in a 1. We get to state B when the input is good, that is, no two consecutive ones, but the last symbol seen is a 1. Notice the only way to get to B is to be in A and then to get input 1. C is actually a dead state. We are there whenever two consecutive ones have been received. We arrive at C for the first time from B, which you recall means the previous input was 1, and in state B we receive a second 1. Once in state C, we stay there because once a string has 1, 1, you can never undo that fact, no matter how many zeros you see. We can also represent automata by tables. Here's our example automaton for strings without consecutive ones, shown as a transition graph in the corner. And we also see a representation of the same automaton as a table. The rows each correspond to one of the states, and the columns correspond to the input symbols. We indicate the final states by putting a star next to their name, and the start state is indicated by an arrow. The entries of the table are the values of the transition function applied to the state that is the row and the symbol that is the column. For example, this entry is C because it is in the row for the state B and the column for input symbol 1, and we know that delta of B and 1 is C. There are two important conventions we're going to use. They let us know the types of things without declaring types. In particular, we can distinguish between strings and characters. We use lowercase letters at the end of the alphabet, W, X, Y, and Z, and sometimes U or V to represent strings. When you see one of these letters, you need to think, aha, that's a string. And lowercase letters near the beginning of the alphabet will represent single symbols. Again, we'll try to remind you at first, but you have to think single symbol when you see one of these letters. The extended transition function delta is a function that takes a state q and a string w of any length, including 0, and tells us where the automaton gets to if it follows a path in the transition diagram from q, where the arcs are labeled by each of the symbols of w in order. That is, we look for the unique path from q whose labels form w. In some materials you will see a hat over the delta to remind you that it is the extended version. However, as we shall see, the extended delta agrees with the given delta when the string w is of length 1, that is, it is a single symbol. Thus there is not really a need to distinguish the extended and original deltas. The definition of the extended transition function delta is an induction on the length of the string to which this function is applied. For the basis, delta of q and epsilon is q. That is, if you are in state q and no input symbols arrive, then you stay in state q. For the induction, suppose the input string is wa. By our convention, w is a string of some length, possibly 0, and a is a single symbol. The inductive rule says that we first see where you get to from state q on string of inputs w. That would be delta of q and w. And then you see where you get from that state, whatever it is, on the last input a. In this example, 0, 0, 1 is split into w, which is 0, 1, and a, which is 1. Then we have to compute delta of b and 0, 1 and see where it goes to on input 1. Now 0, 1 is broken into a string w that is just the 0 and then an a, which is 1. So we need to compute delta of b0 and then see where we get to on input 1. Okay. But delta of b and 0 is a, see, right here. Thus, we can replace delta of b and 0 by the a, and now we have to say, what is the value of delta of a and 1? Well, that's b. Okay, so that's a b, and we replace that by the b there. And then finally, delta of b and 1, that's c. So that's our answer. Delta of b and 0, 1, 1 is the state c. As I mentioned, the extended delta sometimes is given a hat. However, we really don't need to distinguish the two deltas because they agree on single symbols. That is, if we want the extended delta for a state q and a string consisting of one symbol a, formally we treat that string as the empty string followed by the symbol a. Then we have to compute delta hat of q and epsilon, but we know by the basis rule that this is q itself. Thus, delta hat of q and a is the same state as delta of q and a. In fact, I really cheated on the previous slide. I needed delta hat of b and 0, and just went to the table and looked it up as if it were delta of b and 0. Now we see they are in fact the same, so it was no harm, no foul. There are many different kinds of automata. We've seen only the deterministic finite automaton so far, but there are many others. But no matter what kind of automaton, its job is to define some language. We'll use L of A to denote the language defined by automaton A. For a deterministic finite automaton, the language it defines is the set of strings that may take the start state to a final state. Formally, the language of a DFA is the set of strings W such that the extended delta applied to the start state and this W is a final state. For example, consider our running example of the automaton that accepts strings without consecutive ones, and consider the input 1, 0, 1. It should accept the string because it obviously does not have consecutive ones. The start state is A, and if we follow the path labeled 1, 0, 1, we first go to B. Then from B we follow the arc with a 0. That leads us back to A. The third input is another 1, so that gets us back to B again. Since the path from A labeled 101 gets us to a final state, 101 is indeed accepted by the automaton. Now this expression is called a set former. It describes sets, and in particular we'll use it to describe languages. In this example, it's describing the language of the automaton that has served as our running example. The set former starts with a curly brace, and then an expression representing the things we want to put in the set. In this case, the expression simply says that the set consists of some strings W. We know they're strings because of our convention. The vertical bar can be read such that, and then there follows a description of what must be true for something to be a member of the set. In our example, we say that the string consists of zeros and ones and does not have two consecutive ones. Many important facts about automata that we might want to prove are of the form that two sets, typically languages or sets of strings, are really the same. We're going to prove that the DFA we've been playing with accepts the language I claimed it does, the set of binary strings without consecutive ones. So one set is the language of the DFA from our example. And the second set is the language consisting of all strings of zeros and ones without two consecutive ones. I'm going to spend a good deal of time proving this simple result because it will give you all the details of how one proves things about languages. In the future, I'm not going to be so focused on proofs, but I think it is important that everyone go through one of these proofs in all its gory detail. To prove two sets S and T are equal, we generally need to prove two things, that each is contained in the other. That is, we start by assuming W is a member of one, say S, and we use that fact to prove W is in the other, T. Then we start over, and we assume W is in T, and we use that to prove W is also in S. In what follows, we take S to be the language of the DFA we have been playing with, and T to be the set of binary strings without consecutive ones. First, we're going to prove that if W is accepted by this automaton, the one shown in the slide, then W has no 1 ones. Okay, and the proof is an induction on the length of W. It turns out that if we simply try to prove this statement on the slide, we fail, and I'll point out in a few slides what goes wrong. A common trick for inductive proofs is to make a more detailed statement here than you really want because it makes the inductive proof work. Here we need to distinguish whether an accepted string gets you to state A or state B because we need to know whether or not the string ends in 1, even though the conclusion no 1 ones is true in both states A and B. The inductive hypothesis will be in two parts. Part 1 says that if W gets you to state A, then not only is W good in the sense that it doesn't have consecutive ones, but it doesn't even end in 1. Part 2 says that if W gets you to state B, then W is still good, but it must end in 1. Remember, the induction is on the length of W, so the basis case is when W is the empty string, the only string of length 0. We're going to use bars around a string to denote its length. And now, let's prove part 1 of the basis. Delta of A in the empty string is indeed equal to A, but the conclusion is true since the empty string does not have consecutive ones. For item 2, things are a little trickier. It is false that delta of A and the empty string is B, but it is also false that the empty string ends in 1. However, an important principle of logic is that the statement false implies false is true. That is, whenever the if portion of the statement is false, then it doesn't matter whether the then portion is true or not. The statement as a whole is true. Thus, a statement like, if I am Superman, then I wear red undershorts, is a true statement simply because I am not Superman. You don't have to concern yourself with the color of my undershorts. The mathematical term for an if-then statement that is true because the if part is false is that the statement holds vacuously. Now let's address the inductive step. We assume that W is a string of length at least 1, and we assume that the inductive hypothesis, the statements 1 and 2 from the previous slide, about strings that get the automaton to states A or B, is true for strings shorter than W. Let's let W be XA, where by our convention A is the last symbol of W and X is all the symbols, possibly none, up to but not including the last symbol of W. Since X is shorter than W, we assume the inductive hypothesis for X. We're going to prove both statements 1 and 2 for W, which remember we broke up as a shorter string X followed by the last symbol A. Let's start with condition 1. That is, if delta of A and W equals A, then W is good. It has no consecutive ones, and it does not end in 1. How can you get to A by reading string X followed by symbol A? Well, look at the diagram. The only transitions into A are on input 0. That's this and that. So symbol A must be 0. That immediately lets us conclude that W does not end in 1. And furthermore, these transitions to A are only from A and B. Thus X must get us to A or B. Now, regardless of whether X gets us to A or B, we can conclude, using the inductive hypothesis, that X is good. It has no consecutive ones. Thus W, which is X followed by 0, also has no consecutive ones, and it surely does not end in 1. Now for part 2. If delta of A and W equals B, then W is good and ends in 1. There's only one way to get to B. You have to be in state A, and the input has to be 1. Thus, if W equals X followed by A, then X gets us to state A, and the symbol A is a 1. We can therefore conclude that W ends in 1. We apply the inductive hypothesis to X, and we conclude that X not only has no consecutive ones, but doesn't end in 1. Any occurrence of 1, 1 in W would either have to be at the end or lie completely within X. We know it doesn't lie within X by the inductive hypothesis. We know 1, 1 cannot be at the end because X does not end in 1, and A is only a single 1. We conclude that W does not have consecutive ones. Notice that if we don't use this more complicated inductive hypothesis, where we distinguish between A and B according to whether the string X ends in 1, then we cannot make the inductive proof. If we know only that X gets us to A or B, then we might think that X gets us to state A yet ends in 1, in which case W, which would be XA, would have 2 consecutive ones. But we're not done. We still have to prove that T is contained in S. That is, if S is a good string with no consecutive ones, then it is accepted by the automaton. It is helpful to restate what we need to prove in its contrapositive form, which is logically equivalent to the original. The contrapositive of an if-then statement, say if X then Y, is if not Y then not X. We can see why this is an equivalent statement, since if Y is false, it couldn't be that X is true, because whenever X is true, Y is true. In this case, X is the statement that W is a good string with no 1, 1s, and Y is the statement that W is accepted by the automaton. The contrapositive is that W is not accepted by the automaton, then W is not a good string. That is, it contains 1, 1 as a substring. A deterministic automaton has exactly one transition from each state on each input symbol. Thus, any string W gets the automaton from the start state to exactly one state. So the only way W could not be accepted is if it gets this automaton to state C. Notice that the only way to get the automaton to C is for some string X to get it to B, and then for an input 1 to follow. Once in C, you stay in C, so anything can follow the X in 1. We'll call that Y. That is, any string W that gets the automaton to state C must be of the form x1y, where X gets to B. We already observed that the only way to get to B is by a string that ends in 1, since the only transition into B is on 1. Thus X must be of the form z1 for some z. Thus W is really z11y, and we can conclude that if delta of A and W is C, then W is bad. That is, it contains 2 consecutive ones. Now we introduce a class of languages called the regular languages. These are the languages that have a deterministic finite automaton accepting them. That means that the language is exactly the set of strings accepted by this automaton. Soon we shall see that there are several other ways to describe the regular languages, including by regular expressions and non-deterministic automata. While many common languages are regular, there are also many that are not. Intuitively, finite automata cannot count beyond a fixed number. Thus, they cannot do things like check whether they have seen the same number of zeros as ones on their input, or check that parentheses are balanced in an arithmetic expression. For those tasks, we need more powerful mechanisms such as context-free grammars, which we will meet soon enough. Here is an example of a language that is simple to understand but is not a regular language. To understand what this notation is saying, we first need to know that an exponent I on a symbol is shorthand for the string consisting of I copies of that symbol. Thus, 0 to the 4th means the string 0, 0, 0, 0. Thus, we read this set former as 0 to the n, 1 to the n, such that n is equal to or greater than 1, or more verbosely, the set of strings consisting of n zeros followed by n ones for some n equal to or greater than 1. The strings of the language L1 are thus 0, 1, 0, 0, 1, 1, and so on. Here's another example of a non-regular language, the set of strings that are balanced parentheses. The strings of balanced parentheses are those that can appear in an arithmetic expression. For example, the string 0 of left paren, right paren, can appear in an expression like a plus b times c. Or this string can appear in an expression like a plus b times c plus d. Examples of strings that are not balanced are the right paren followed by a left paren. This is not balanced because no prefix of a balanced string can have more left parens than right parens. Obviously, there is no arithmetic expression that has this sequence of parentheses as its sole set of parentheses. Also, 3 lefts followed by 2 rights. It's not balanced because it has more left parens than right. However, regular languages are common. For example, in each language there is a format for floating point numbers, and this format can be quite complicated with optional e's or decimal points and strings of digits that could be empty. But in all programming languages I know about, the set of strings that represent some floating point number is a regular language. This is a very interesting case illustrating what finite memory means. We want to know if a binary number is divisible by 23. We're going to read the bits high order first. But if we have only finite memory, how can we remember exactly what sequence of bits has been read, since the sequence can grow very long? But there is a trick. We don't really need to remember everything about the bits read. It is sufficient to remember what the remainder is when divided by 23. Thus, we'll have 23 states, 0 through 22. These correspond to the 23 possible remainders when an integer is divided by 23. The start state is 0 because we interpret the empty string as representing the number 0. That may be a bit of an assumption, but nothing else makes sense, and treating it as 0 makes everything work out right. State 0 is also the only final state, since we want inputs that leave a remainder of 0 when divided by 23. We're going to assume that things are working right after reading a binary string w. That is, w takes state 0 to the state that is the correct remainder when w is divided by 23. I'm using the C-style percent operator to denote the remainder. You can read the percent as modulo or mod, which is just another way of saying the remainder when divided by. The transition from each state I on input 0 is to the state that is the remainder of 2i divided by 23. To see why this works, we know that I equals 23a plus b. For some integer a and for some integer b in the range 0 to 22. That is, b equals I mod 23. Then 2i is 46a plus 2b. Since 46 is divisible by 23, 2i mod 23 is just 2b mod 23. That is, when we divide by 23, we can just get rid of the 46a. We know it will leave a remainder of 0. Thus, we can take the state b, which is the remainder, double it, subtract 23 if it is 23 or more, and that gives us the new remainder and therefore the new state. We never need to know what a is, and we never need to know I exactly. For the same reason, when a 1 arrives at the input, we can go from state I to the state that is the remainder of 2i plus 1 when divided by 23. For example, twice 15 is 30. So from state 15, we go to the state that is the remainder of 30 divided by 23, or state 7, when the input is 0. From state 11, on input 1, we go to the state that is the remainder of twice 11 plus 1 divided by 23. That's state 0. So whenever a string gets you to state 11, that is, the string leaves a remainder of 11 when divided by 23, that string followed by a 1 must be divisible by 23 and therefore must be accepted. Interestingly, another regular language is the set of all the binary strings that if we read the strings in backwards, that is low order bit first, they form a binary integer that is divisible by 23. And there's nothing special about 23. It could be any number in both this example and the previous one. So for example, 0110100 is in this language because when we reverse it we get 001011110, which has the value 46 in decimal, and 46 is of course divisible by 23. It is really tricky to design a DFA to accept this reverse language. However, there is a theorem, which we shall see soon, that says if a language is regular, then its reversal, what you get by reversing each of its strings, is also a regular language. The proof of this theorem will let us construct the DFA for the reverse language from the DFA we just saw. Today we introduce the nondeterministic finite automaton. We're going to use the subset construction to show that every language that can be recognized by any nondeterministic finite automaton is still a regular language in that it can be also recognized by a deterministic finite automaton. We're then going to add something to the nondeterministic automaton called epsilon transitions that allow sort of spontaneous jumps from state to state, and we will in fact show that these automata, even though they look more powerful, also can recognize only the regular languages. A nondeterministic automaton has the ability to be in several states at once. A transition in a nondeterministic automaton is from some state, say Q, on an input, say A, it can go to several different states. So we can have several transitions all labeled A. And this is the thing that allows the automaton to, in a sense, guess, to be non-deterministic. It can go from state Q to really any of these states, and therefore it actually goes to all of those states at once. Okay, like the DFA, a non-deterministic finite automaton, or NFA as we will call it, has one start state where a computation begins. The NFA can have any number of final states, and an input is accepted if any sequence of choices leads from the start state to some final state. The intuition is that the NFA is allowed to guess which way to go, but it is able always to guess right, since all the guesses are followed in parallel, and the NFA gets credit for the right guesses, no matter how many wrong guesses it also makes. In our example of a non-deterministic finite automaton, the states are squares of a chessboard. In general, you can occupy several different squares at a time. In a red move, which we represent by the input symbol R, you get to move to any adjacent red square. So in effect, you replicate yourself and move to all of them. Similarly, if the input is B, you can move to any adjacent black square, So in effect, you move to all the black squares. The question we ask is whether the given sequence of R and B inputs can get you from the start state, which will be the upper left corner, to the one final state, which is the lower right corner. The answer is yes, if any sequence of choices we get with each input leads us from the upper left to the lower right. It is not necessary that all such choices do, and in general there will always be some choices that lead us astray. Okay, so here's our example. The chessboard will be rather tiny. It's only 3 by 3 instead of 8 by 8, but the ideas are all the same. Okay. Now, using the moves which I have summarized in a transition table, but which follow the intuition that I gave you, we're going to examine the sequence of inputs RBB. That is one red move followed by two black moves. We'll start in the start state, state 1 only. So we're going to show state 1 there. Okay. Now, we get an R input, so we can move to any of the red squares adjacent to square 1. Or in terms of the transition table, here's the row for state 1. We look under R and we find states 2 and 4 are the possible moves. Okay, and notice that adjacent really means one king move, so that from state 1, let's say you can go to 2, 4, or 5, obviously only 2 and 4 on a red move and only 5 on a black move. Okay, so after reading the R, we go from state 1 to states 2 and 4. Okay, so now we're in states 2 and 4, and B comes in. So what do? Well, from state 2, we can go to 1, 3, or 5. You can figure that out either by noticing that 1, 3, and 5 are the adjacent black squares, or you can just look it up on the table here in row 2. The black moves are 1, 3, and 5. Now how about state 4? Well, from 4 you can go to 1, 5, or 7 on a black move. Some of those states were already listed, but the point is that between 2 and 4, the states you can get to are 1, 3, 5, and 7. Now, that's all for the first B. Now the second B comes in, and from 1 you can only go to 5. From 3, same thing, you can only go to 5 on a black move. Now from 5 you can go to a lot of states. You can go to 1, 3, 7, and 9. And from 7, again, you only go to 5. So after reading the RBB, you are in fact, all the odd-numbered states, or actually all the black squares. Since 9 is the accepting state, we say that RBB is accepted by this automaton. The fact that it's also in states 5, 1, 3, and 7 are not relevant to the question of whether it's accepted or not. Here are the components of an NFA. They look exactly the same as for the DFA, and we'll typically use the same letters to represent them. The big difference is in the type of the transition function, and we'll see that on the next slide. For the NFA, delta of state Q and input A is now a set of states, possibly empty, rather than a single state as it was for the DFA. The extension of delta to strings is a bit more complex. The basis is still easy. Delta of Q and the empty string is just the set containing Q, since the only state you can reach on no input is the state you are in. For the induction, suppose we start in state Q and we read string W followed by symbol A. We first compute delta of Q and W, the set of states you get from Q by following W. So let's, from Q, let's say following paths labeled W, we might get to states P1, P2, and so on. Okay, then for each of these states, say P1, P2, and so on, we're going to use the given delta function to find the set of states they each get to on A. So let's say P1 might go to these two states, I don't know their names. P2 might also go to that one, and several others, and so on. You find all the states you can get to, but always on transition labeled A. And the resulting union, this set, is delta of Q and WA. Okay, the language of a non-deterministic automaton is simply the set of strings that it accepts, that is, the set of strings W such that when you compute delta of Q, Q naught and W, that's Q naught is of course the start state, when you compute delta of Q naught and W, you have a set that contains at least one final state. Okay, the language of the non-deterministic automaton that we designed to represent moves on a chessboard is actually quite tricky to describe. For strings consisting only of B's, it's easy. You start in only in the state 1, and on the next move with B, you only go to state 5, so you're only in the set containing 5. Another B, if you'll notice, will take you from 5 to 1, 3, 7, and 9. So now, after the second B, you're in 1, 3, 7, and 9 only. The next B, well, each of 1, 3, 7, and 9 only have B as an adjacent black square. Their other adjacent squares are red. So after 1, 3, 7, 9, you are now in just the set 5. And from 5, you go to 1, 3, 7, 9, and so on. As a result, you accept all the even length non-empty strings. That is BB, BBBB, 6 B's, 8 B's, and so on. And you don't accept strings B or BBB, and so on, the odd length strings. Okay. It's less clear what happens when there are R's in the input. Obviously, an accepted string must end in B because only state 9 is accepting, and you only get there on a B move. But I'll leave it to you to figure out exactly what strings with one or more R's are accepted. Okay. In a sense, a DFA is an NFA that just doesn't have any non-determinism. Formally, given a DFA with a transition function, which we'll call delta sub D, you can create an NFA with the same states and inputs as the DFA and the same start and final states. The only thing different about the NFA is that the form of its transition function is what it has to be for an NFA. It gives you a set of states rather than a single state. But that set of states in delta N will be exactly the one state that delta D gives you for a given Q and input A. As a result, the NFA, after reading some sequence of inputs, is in the set of states that's always a singleton. It always contains only the one state that the DFA is in. Okay, so that says any language accepted by a DFA can be accepted by some NFA, and in fact the NFA really looks the same as the DFA, and it almost is the DFA. Okay. Surprisingly, for any NFA, there's a DFA that accepts exactly the same language. And the proof is called the subset construction, and this construction was the thing that, as a graduate student, convinced me that there was something to computer science theory. It had only been discovered 5 years before, and it boggled my mind to see a construction that, while it could be described easily, resulted in something that could not be grasped. Okay. The problem is that the number of states of the DFA that you get from an NFA can be the number can be exponential in the number of NFA states. Now, if the NFA has 3 states, the DFA can have 8 states. That's not a big deal. I can visualize an 8-state automaton. But if the NFA has 10 states, The DFA could have 1,000 states, and that's already becoming quite hard to imagine. And if the NFA has 20 states, which is still something we can visualize, the DFA can have 1,000,000 states, and we're completely lost, even though we know the DFA exists. Oh, and by the way, the situation is not nearly as bad in practice as it looks in theory. Many of the non-deterministic automata that you construct in things like compiler design, when you convert them to a DFA, the number of states doesn't really grow much at all, if at all. In fact, the chess NFA that we just introduced actually has an equivalent DFA with fewer states, as we shall soon see. So let's start with a typical NFA. It has the conventional names for the components, although we'll use delta n for its transition function to distinguish it from delta d, which will be the transition function for the equivalent DFA that we're going to construct. Now, in the DFA, states are represented by 2 to the q, which is 2 to the q is a mathematical notation for the power set of q, that is the set of all subsets of q. Okay. Notice that if a set q has n elements, then its power set has 2 to the n elements, so the notation sort of makes sense. So the important point to remember is that the DFA states are actually sets of states of the NFA, and there can be an exponential number of them compared with the number of states in the NA. The inputs of the DFA are the same as the inputs of the NFA. That's the set sigma. The start state of the DFA is the set containing the start state of the NFA. Okay. Remember that the states of the deterministic automaton are sets of states of the non-deterministic automaton. Okay. Thus, the start state, which is a single state of the DFA, is written as a set of states of the NFA. Of course, this set contains only the start state of the NFA. Okay. Then, the final states of the DFA are all those states that they're thought of as sets of states of the NFA contain a member of F. Remember, F is the set of final states for the NFA. Just to make sure we understand what's going on, the DFA states have names that look like sets of states. However, they are single objects. Okay. An analogy that might be useful to make is with a class of objects in a language like Java or C++, whose values happen to be sets of objects from some other class. Okay. The transition function delta d is defined by delta d applied to, now again, this is not a set of, this is a set of NFA states, but this is a single state of the DFA, and input A is the union over all all the states Q1 through Qk of what you get when you take the delta n, or there's the transition function of the non-deterministic automaton, and apply it to that Qi and A. So you have Q, here's Q1, here's Q2, and you see where you get to on A, and like that. And so on. And this set of NFA states is the name of the DFA state that you get to when you go from this state of the DFA on input A to the next state of the DFA. Okay, we're going to, as an example of the subset construction, do a lazy construction of DFA states. That's generally much better than assuming we need all the subsets of NFA states. Okay, we're going to start, of course, we know we need the set containing the initial state, so we surely need, as one of the DFA states, the set containing 1, because that's the initial state of the NFA. But we're only going to create rows for states when we are sure that we need them. Okay, so obviously we need the start state of the DFA, which is the set containing 1. So we'll begin the construction with a row for the set containing 1. Now, from the NFA table, which I've outlined here in red, we know that on R, 1 goes to 2, 4, and on B it goes to 5. And since this set is a singleton, that's all we need to know. So we know immediately that in the DFA, the set containing 1 goes to the set containing 2, 4 on R, and set containing 5 on B. Now, I've put these two sets, I've made rows for them in the table. I haven't filled out the rows yet, but we know that we're going to have to because they obviously are states that you can reach from the start state of the DFA. Okay, here we've filled out the row for the DFA state whose name is set containing 2, 4. Okay. Well, on input R, we look at this is the NFA table. We look at the things marked in red, that is, on 2, so from 2 on input R, you go to 4 and 6, and from state 4 on input R, you go to 2 and 8. So from the set containing 2, 4 on R, you go to 2, 4, 6, 8. Again, this is a single state of the DFA. And since I haven't encountered the state before, I now create a row for it, reminding me that I'm going to have to figure out what its transitions are sometime in the future. Let's see, again, from state 2, 4 on input B, you just look at where the NFA goes on those two states, and you take the union of 135 and 157. That's 1357, and that's in there. And I also put it here because I'm going to have to figure out its row in a minute. Now we fill out the row for 5. Again, that's fairly easy. You just look at the row for 5 on the NFA table, and you enter the states right there. 2, 4, 6, 8 we've seen already, so we don't have to create a row for it. 1, 3, 7, 9 has not been created, so we will create it now. And I've also started because notice that is a final state of the DFA. It has the final state of the NFA, state 9. Okay, now for 2, 4, 6, 8, again, I've in the NFA table, I've put in red the relevant rows. For R, I just take the union. I've got 4, 6, 2, 8, 2, 8, 4, 6, so the union is 2, 4, 6, 8. That's a state I've seen already, not interesting. On B, I've got 1, 3, 5. I've got 1, 5, 7. I've got 3, 5, 9, 5, 7, 9. The union of that is 1, 3, 5, 7, 9. That's a new state, so I add it to the list of rows I need to construct. And by the way, it's also a final state because it contains 9. Okay, here's the row for 1, 3, 5, 7. Again, the same process. You again get 2, 4, 6, 8 on R, and now you get 1, 35, 7, 9 on B, and these are both states you've seen, so we add no new rows. For 1, 3, 7, 9, we just compute its entries. Perhaps the only interesting thing is that on a B, all of 1, 3, 7, and 9 go to only B, so only 5 on B. So what you get is the set containing only 5. That is a state that we've seen before, as of course is 2, 4, 6, 8. So we don't have to add any new states. And finally, 1, 3, 5, 7, 9 also yields no new states. And so we now have completed the entire transition table for the DFA. Notice it only has 7 states, while the NFA had 9. So it actually shrunk the number of states. Again, you have to be rather lucky to do that, but it does happen. We're going to prove that the NFA and the DFA we construct by the subset construction are equivalent. That is, they define the same language. We must thus show that if one accepts a string W, if and only if the other does. That is, the two languages are each contained in the other, and therefore they are the same. Now, notice that delta n is a set of NFA states. Delta d, on the other hand, is a single state, but its name is a set of NFA states. So it is quite reasonable, at least it's an interesting pun, to argue that this as a single state is the same as that as a set of states. For the basis, let W be the empty string. Then delta n of Q0 and the empty string is the set containing Q0 by the basis rule for extending the delta for non-deterministic automata. And delta d of the set containing Q0 and the empty string is the set containing Q0, again, by the extended delta rule for deterministic automata. For the inductive step, we'll assume the inductive hypothesis that the states of the DFA, that the DFA and the NFA get to on string W are the same sets for all strings shorter than W, and we'll prove the statement for W itself. Okay. W is of length at least 1, so we can write it as string X followed by symbol A. And we can assume the inductive hypothesis holds for X, because it is clearly shorter than W. That is, we're going to assume that delta n of Q0 and X is delta d of set containing Q0 and X, and we'll call that set S. Let T be the set of states the NFA can get to by starting in state S and following a transition on A. So that is, we have, let us say, here's set S of states, and coming out of various of these states are transitions on A. Okay, by the rule for the extended delta for NFAs, the set T of all the states that you get to is delta n of Q0 and W. By the subset construction, we also know that delta D of S and A is T. Thus, delta n of Q0 and W and delta D of Q0 and W are both T. The latter, of course, is by the extension rule for deterministic automata. That is how you compute the extended delta. So we have therefore proved the inductive step. Okay. We are now going to add an additional capability to NFAs, the ability to make a spontaneous transition on epsilon, that is, without using any input. We just saw that the NFA, while it can be a convenience in designing automata, still accepts only regular languages. The same is true for the new model, which we'll call epsilon NFAs, but they can be a real convenience in constructing automata, and yet they still accept only the regular languages. Here's an example of an epsilon NFA. The transition diagram has some arcs labeled epsilon, and we can follow any such arc without adding to the sequence of inputs that the automaton has processed. That is, epsilon is invisible as far as input strings are concerned. Okay. We also see the transition table for this automaton. Notice it has a separate column for epsilon, but epsilon is not an input symbol. It's not a member of the input alphabet. For example, from the start state A, let's look at A, there is only one transition on 0 to E, and that's why you have set containing E over here. There's only one transition, that's to B, on input 1, so that's why you have set containing B there. And there are no transitions out on the empty string. So we have the empty set symbol represents the transitions from A on epsilon. It's not an input. It represents spontaneous transitions. Let's look at E now. On 0, there's a transition to F, and only to F, so you get set containing F there. There are no transitions at all from E on a 1, so you get the empty set. Okay. And on epsilon, you have transitions to both B and C, so that you have set containing BC at that entry. Okay. Notice that if we are in state E and the input is 1, then we can spontaneously go to B on epsilon, and then on the 1 wind up in C. Okay. We can also go spontaneously from E to C on epsilon and wind up in D on input 1. Okay, now to do the conversion of epsilon NFAs to regular or ordinary NFAs, we need to have the notion of the closure. The closure of a state Q, which we're going to write as CL of Q, is the set of states we can get to starting in Q and following only epsilon transitions. So, for example, from A, you can get nowhere else on epsilon, right? If you're here, there are no epsilon transitions out. As a result, the closure of A is just the set containing A. Of course, you're in A to begin with, so you can stay in A. So closure of a state always contains at least itself. The closure of E is trickier. Okay, we start in E. Surely we can reach E. Then there are epsilon transitions from E to B and C, so we can surely get to B and C. But now we have to see where can we get to from B and C. Well, C doesn't have any epsilon transitions out, so we can't get anywhere else. But B also has D, a transition on epsilon to D. D has nowhere else to go on epsilon. So the conclusion is that the closure of E on is all of B, C, D, and E. And that's what we've written here. Then we also are going to need to apply the closure operator to sets of states, and the definition is quite simple. The closure of a set of states is just the union of the closures of each of those states. Now, we need to describe the operation of an epsilon NFA by defining the extended delta. And again, it's intended to tell us about where we can get from a given state following a path labeled by a certain string W. However, epsilon, the empty string, is invisible along paths, so W only involves the real input symbols of the automaton. As a result, we follow paths that are labeled by real symbols of W, but with arcs labeled epsilon interspersed as much as we like. Okay, so for the epsilon NFA, delta hat of QA is not the same as delta of Q and A, because delta of Q and A does not include any epsilon transitions. So we're going to keep the hats on the extended delta when we need them. Okay. So for the basis, delta hat Q and epsilon is the closure of the state Q. So it's not just Q. If you can reach anywhere from Q on epsilon, then that's included in the closure and therefore in the delta hat. For the induction, suppose the input is string X followed by symbol A. Start by figuring out what delta hat of Q0 and X is. Say it is a set of states S. Okay. For example, let's suppose that X is BC. Then we might start from Q0 and we'll follow paths labeled epsilon and then a B, and then maybe more epsilons, possibly none, to a state where we follow a C, and maybe even then more epsilons. Now, suppose this takes us to a set of states S. To compute delta hat of Q and X followed by A, we look at all the states in S. We find all the A transitions, no epsilons now. We then have to take the closure of these states, that is, we follow all the epsilon paths. And finally get to the state that is this set of states is delta hat of Q and XA. Here is an example. This is the automaton that we've been playing with. I say delta hat of A and epsilon is the closure of A. That's the basis rule. And that's just set containing A, because A doesn't get you anywhere on epsilon. Now, I'd say the delta hat of A and 0 is the closure of E, which is B, C, D, and E, as we discussed earlier. Why closure of E? Because when we already determined that the closure of A is A, and on 0, the only place you can get to from A on a 0 is E. So we have to close E. Now, delta hat of A and the string 0, 1, I claim is closure of C and D, which actually is just C and D. Why is it closure of C, D? Well, look, we already know that delta hat of A and 0 is the set containing B, C, D, and E. Okay, so we're sort of here, 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 and here. Now, on a 1, where can I go from any of those states? Well, from E, no place. From D, no place. From B to C, and from C to D. So the only places you can get to from B, C, D, and E on a 1 are C and D. So that's why we start with C and D. We take the closure. Now, neither C nor D have any epsilon transitions out, so we conclude that delta hat of A and 0, 1 is set containing CD. What that means is, if you look at, starting in A, all the paths labeled 0, 1, with as many epsilons as you wish thrown in the middle, those paths lead you only to C and D. That is, there's this, there's this, and there is this. Okay, and that's it. Okay. Finally, the language of an epsilon NFA is defined in the expected way. For any string W, you compute the extended delta of the start state and that string W. And if you see if any of the resulting set of states is a final state, you accept W if so, and if not, then not. Okay, we now want to show that the NFA and epsilon NFA models yield the same languages, the regular languages, of course. One direction is easy, since an ordinary NFA is an epsilon NFA that happens to have no transitions on epsilon. But proving that for every epsilon NFA there is an ordinary NFA that accepts the same language, we're going to have to get rid of the epsilon transitions. We do that by combining them with the next transition on a real input. Okay. If you're following the text, you should notice that this construction is somewhat different from the one in the text, but both constructions work. Here, we'll have to change the set of final states, while the one in the book doesn't, but this construction is, I believe, a bit simpler. Okay. This is a picture of how we iron out the epsilon transitions. We start from a state, okay, here, and we follow all the epsilons we can using the closure operator, and I'm sort of imagining that the yellow area represents paths that are labeled only by epsilons. We then follow all the transitions from any of the states we reach on a real input symbol A. The ordinary NFA is able to get to, on input A, any of the states that can be reached using these transitions of the epsilon NFA on input A. That is, the ordinary NFA will have a transition from here to each of these states on input A. Now, since we don't close the states after transition on A, we have to make additional final states, those that can reach a final state on epsilons only. So, for example, if this state might not be final, but it might be able to reach by epsilons some final state. If so, that is, this is a final state of the epsilon NFA, but in the ordinary NFA we're constructing, we're going to make this state be final. Because in effect, it has the power of a final state in the epsilon NFA. Whenever you get there, epsilons will take you to a final state, so you know that whatever got you here will be accepted by the epsilon NFA, so you want the ordinary NFA to accept it as well. We're going to start with an epsilon NFA that has the usual components, Q for states, sigma for inputs, and so on, but we'll use delta E for its transition function. Okay, and we're going to construct an ordinary NFA with the same set of states, same input symbols, same start state, a different set of final states, perhaps F prime, and its transition function will be called delta N. Okay, now, the way we compute delta N of Q and A is as follows. We're going to start in state Q. We're going to close Q, that is by following epsilon paths, to get to some set of states S. Okay. Delta N of Q and A is take all the states in S, we find all their transitions on A, and this is the set of states that is delta sub N of Q and A. Okay. That is, in the ordinary automaton, Q gets you on A anywhere that the epsilon NFA can get you by following 0 or more epsilons and then an A. Okay. Now, prime, the set of final states of the ordinary NFA, is the set of states Q such that the closure of Q contains a state of F. That's the thing that, again, allows you, if there's an epsilon path to a final state, then this state gets the same accepting power that wasn't needed in the epsilon NFA. Okay, we're not going to prove this, but the idea is that the NFA on any input W enters the set of states the epsilon NFA enters on the same input using epsilon transitions anywhere it likes, except at the end, after reading all the real inputs of W. However, state P in delta N of Q0 and W is a final state if, in the epsilon NFA, P can get to a final state following only epsilons. Okay. Thus, the fact that the equation holds, that is this equation here, is enough to say that W is accepted by either both or neither of the automata. That is, if delta E contains an accepting state, then delta N of Q0 and W will contain a state which has also been made accepting because it can reach on epsilons an accepting state of the epsilon NFA. Here's the epsilon NFA we used before as an example, and the NFA, ordinary NFA, that we construct. The interesting changes are marked in red. So first of all, here are all the non-trivial closures. That is, the closure of B, because B goes to D on epsilon, the closure of B is B and D. And the closure of E, which we've worked out before, is, E goes to B and C, B goes to D, so E can go to B, C, D, and E. Okay. In the NFA without epsilon transitions, we need to change the transition from E on input 1. And the reason is that we first take the closure of E, which of course is B, C, D, and E, and then we ask, where can I get to from those states on a 1? And if you look at the epsilon NFA from B, C, D, and E, all you can get to are C and D. Okay. So we put C and D. It becomes the entry there, whereas in the epsilon NFA it was the empty set. You can see that. Okay, the transition from E on 0 actually doesn't change. The reason is that B, C, and D have no transitions on 0. So the fact that we can get to them on epsilon doesn't help us when the input is a 0. Okay, finally, since the closures of B and E include the final state D, they become final states as well as D in the ordinary NFA. And that's the entire construction. So, we now have 3 different formalisms for describing languages: the DFA, the NFA, and the epsilon NFA. They look progressively more powerful, and in fact they are more powerful in the sense of the things they can do. But in fact they give us exactly the same class of regular languages. Very soon we'll see a 4th formalism called regular expressions that look quite different from these, but in fact also give us exactly the regular languages. So we might be getting the idea that the regular languages are quite a natural class of languages, and indeed they are. We should notice that the added power of NFAs and epsilon NFAs are quite useful. For example, we shall talk about designing automata to recognize sets of keywords, say the reserved words in C or some other programming language. That is an important task for building a compiler for the language. We could design a DFA for the task, but it's much easier to start with simple DFAs for each keyword. It's just a chain of states. Say for else, it's just an E, an L, an S, and an E, and of course that's a final state. Okay, so that's how you recognize the keyword else. Then we'll connect them all with epsilon transitions from a single start state. So you put an epsilon here. This becomes the start state. And you'll have epsilon transitions to a lot of these chains for all the keywords. And they, of course, all end in a final state. And that's all there is to it. You've got an epsilon NFA. And then we're going to convert them to a deterministic automaton, because the deterministic automaton is necessary for if you want to actually execute an automaton. That is, only a DFA can be implemented. No one has yet invented a non-deterministic computer, although I've heard that Intel is working on it.